some of you maybe have already tried looking into it. So basically, TensorFlow is software library, which is open source and free. And it's mostly used to build deep learning models. So we're in the area of machine learning. And actually, TensorFlow, it's also used even with other machine learning algorithms, but its main application is actually deep learning. So deep learning is a subset of machine learning, and it takes into account all those models based on artificial neural networks. And these are actually deep models. So it's quite a complex network of artificial neurons. So this is what we mean by deep learning. And TensorFlow is actually great to learn about deep learning and code in a very easy way and very simple and fast way a machine learning model. So what are the advantages of using TensorFlow? Well, first of all, it's open source and free. You find a lot of code online which can help you if you want to build some very specific architecture. There is a big community that is helping you. But also, the great thing of TensorFlow is that it's quite easy because it's a very high-level abstraction of many more complex algorithms that are built behind it. So TensorFlow, we said, is a library, and it provides you some abstractions of deep learning models, which otherwise you'd have to build on your own. And it's a lot of algebra, calculus, quite complex. So coding it from scratch every time you want to build some deep learning model isn't quite straightforward. So the great thing is that we do have TensorFlow, and we can write in very simple, very few lines of code, a model working and predicting, making predictions from your data. So what we see in this image, it's actually the great advantage is that you can process data in parallel through TensorFlow, and you don't even have to specify it by code. It's going to do it automatically. And this is very useful in deep learning because we have complex model with a lot of parallel computation. So it's going to save us a lot of time. And usually these models are going to be run on GPUs. And this is going to be done in a transparent way by TensorFlow. Usually the data processing part will be handled on a CPU, while the actual computation in the data flow through the network and the backpropagation is going to be computed using GPUs. So the great thing of TensorFlow is this high-level abstraction, but also the fact that it's cross-platform. And it's quite straightforward to use. You can open a Jupyter notebook and code using Python and just import TensorFlow. So the TensorFlow we're going to be looking at today is TensorFlow version 2. Version 1 is quite different to use and a bit more complex in terms of even specifically the lines of code you have to write to perform a training task. And TensorFlow 2, the great advantage is that we're going to be using the Keras API that is provided within TensorFlow. So what is Keras? It's essentially a set of functions that are able that you can use for both data processing and also for model training. So we're going to be using this today. And to solve which problem? Well, as some of you anticipated it, we're going to solve a classification problem. So what we're going to do is, starting from a data set of images, trying to predict the class that they belong to. So the data set we're going to be working on is the fashion MNIST. So it's a data set of images of clothing, pieces of clothing. So we have shirts, trousers, sneakers, and these are actually our labels. So the output of our model will be a class. So we're going to see from an image whether it is a shirt, trousers, sneakers, and so on. So this is a fairly small data set. We have 70,000 images, and it's great for learning. So if you want to try out, like, for example, a different architecture or make a few small experiments to understand if you have learned correctly something, it's a great data set to start from. There's also another similar version of it. There's the MNIST without the fashion part. It's actually a data set of handwritten digits. So the goal is classifying the image to which digit it belongs to. And also this, it's great to start putting your hands on in code. And the great thing is that it's available through Tensorflow, so you can easily pull the data set and load it onto your notebook and start working on it. So this is it for the introduction. So for this class, I'll let it over to Jacopo to show you out how to actually implement this model. So what we're going to do is, as we anticipated, we're going to be using Collab, which is essentially a Jupyter notebook online. And the great thing is that you can use some hosted GPUs, so you don't have to train anything on your physical machine, because machine learning, and especially deep learning models, they require GPUs to be able to be performed, to be trained in a reasonable amount of time. And the majority of computers, your personal computers, do not have GPUs. So great thing of Collab is that it's free. You can use you have to use your Google account to access it. And you open a Jupyter notebook, and then you can already work on TensorFlow. So I'll leave it over to Jacopo. We're going to share this link in the chat. And we're going to start. Yeah. Okay, Jacopo already shared it. So we're going to start directly, put our hands on the code. But for any question, just feel free to type it into the chat. And both I and Jacopo are going to help you all throughout the problem.
All right, great. I hear the echo, Virginia, so thank you. All right, so it seems like my connection isn't the best, but that's why I won't put my video on. You can hear me well, I'm quite sure you can anyway. All right, so let's get started. I would say if you click on the link, this is what you will see. So I want to get this straight, because it's the first of 3 workshops that we will have. We'll do 2 today. One is on image classification. The other one is on transfer learning, still on image classification. And then the last one, we'll do it on Thursday, and Virginia will lead it. So on image captioning. So again, as Virginia said, feel free to ask questions in the chat. Big disclaimer, nobody knows everything, so we might not be able to answer. We'll probably not be able to answer all of your questions, which I'm sure will be super interesting. And so please already consider that and excuse us for that, but nobody knows everything. I really am sure that some of you will be way better, even better scientists than we may be. And so I really hope that this could be the start for many of you of your journey in machine learning. And I really hope that this could be really helpful and inspirational. So we won't go super fast, and we won't even go super slow. And that's because our audience is quite diverse, and we want to make sure everybody feels included and can follow the workshop nicely. So if we're going too fast or we're going too slow, please let us know. And yeah, I would say with this being said, let's get started. So the first thing that you will see once you click on the link is this, and you want to click on Run in Collab, Google Collab. So please do that, and this should open up for you. If it does, please type in the chat and somebody will be able to help you. Make sure to be signed in with your Google account. I'm sure you all have a Google account, and we already mentioned that you should have this for our workshops. Well, the first thing you want to do is you want to connect to the Google supercomputers, essentially, right? So what's happening is we are initializing a connection to Google computers that are in the cloud, so that the code that we run does not run on our machine, but it runs on Google's computers. And so by doing this, of course, unless we have a super powerful machine at home, then we'll have more compute power, more RAM, which is quite important, not a lot for this specific workshop, but perhaps in the one that we will see on Thursday, it may actually be very helpful. So make sure you're it. All right. So I would suggest you to follow so to walk through the workshop together with me. If in case like you don't know anything about machine learning, if you already have some experience, I would also suggest you to while I speak, to try and read and have a better understanding also of the code that we are analyzing. So I'm assuming that the zoom level of my screen is good enough for everyone, but if you want, I can make it a bit even more zoomed. All right. So let's get started. So we're coding in Python. I'm assuming that most of you know Python. Make this a bit bigger, actually. And so it will seem to you that be reading much of what's already written there. And that's because the people who created this tutorial actually did a great job. But we're going to try to understand almost every line of code that's written here. So the first thing that we need to do is to actually import our libraries that are essentially TensorFlow, and of course Keras, that's part of TensorFlow. And then NumPy and Matplotlib, there are two Python libraries that are useful for data science scenarios and yeah, anything literally like machine learning and data science. So let's go ahead and do that. And once we've done that, we're now ready to import our data set. So again, just to repeat this, we're going to be using the fashionist dataset, which contains 70,000 grayscale images divided in 10 categories. Right. So, okay, I can zoom out a bit more. Let me also close this. So this should be fine. All right. So as you may see, these are all images of clothing, and these are categorized into 10 classes. So we may see some shirts here, some trousers, some other shirts, and all of this, some shoes, some bags, right? And this data set is actually by Zalando, you know, the company that sells, I'm sure you know it, and you probably bought something off of it also. So what we're going to do now is we're going to load the data set, as you may see here, TensorFlow Keras.datasets, the fashionist dataset that's already in TensorFlow. We're going to load it into this variable. And then what we will be doing is we're going to split our dataset into the training set and into the test set. Now, I'm assuming that you all know what a training set and a test set is, right? Can you say yes or can you say no in the chat? That would be great, so that we can also go faster. Yes, great, fantastic. All right, so we just did that. We downloaded the data and we split it into the training set and to the test set. And what is the difference between train images and train labels? Test images, test labels. So we have that the train images are actually the images and the labels are actually the labels. And so we'll have an image such as a shirt, and then its label that is the class, or in this case, the shirt, right? This is quite obvious, but just wanted to make sure that we're all on the same page. And so what happens here is that the images are represented as a 28 by 28 arrays. So essentially matches that have pixel values ranging from 0 to 255. That is essentially the color, right? And the labels instead are an array of integers, each one assuming a value from 0 to 9, right? So we have 10 classes. So as you may see, these are the classes that we are considering. All right, so this should be quite straightforward. We assign class names for human readability, and we can see by exploring the data, that's essentially what Virginia was doing today during her workday. We explore the data and we look at the shape of our data. So you may see train images is a NumPy array, and a NumPy array is not necessarily a one-dimensional array, right? So essentially a list. It can have multiple dimensions. So in this case, we have 3 dimensions, right? Where we have the number of images, and each image is represented by a matrix that is 28 by 28. So you can imagine this in 3 dimensions, right? So as you may see, also the labels are 60,000 because we have 60,000 images. And each label, as you may see, is between 0 and 9, as we already said. The same happens for the test images, that instead of being 60,000 are 10,000. So why do we want the test dataset to be less than the training dataset? Well, that's because we want our model to be able to train itself on quite a lot of data, and then we want to test it on a few data that is not too little. Otherwise, we couldn't really have a significant test, but also not a lot because it's not necessary. So as we remember from our first seminar, after we explored the data, we want to pre-process it. And so let's actually go ahead and inspect one of the images that we find in our data set. So in this case, what is this? This looks to me like a shoe, maybe, right? So this is one of the images that we will be feeding into our model. You can see we have 28 pixels here and 28 pixels here. So this is the matrix that I was talking about. And you may see how each pixel has a value that goes from 0 to 255. What we will be doing is that we will be scaling our values. And scaling is quite important in machine learning, because it is important to have values that are small and are of the same scale, so that our model has better performance. And there are many reasons for that, but we won't investigate those today. And so we divide each value by 255, right? So that each value is between 0 and 1. So now we can plot again our some of the images that we have in our training set. As you may see, this is what happens. We have our image and the label, right? So I'm guessing there are no significant questions at this point. If there are, please throw them in the chat. All right, so I guess we're ready to train our model. So as you may see, until now, we've done very important steps in the machine learning pipeline, that is the data exploration and the data preparation. And they were super quick to do because our problem is super simple, I would say. We have some data that is not very sparse. I would say it's not very generic, right? We only have 28 by 28 pixels. And it's also not colored data. The data is black and white. And so the values that are possible are only from 0 to 255. So we're not dealing with a lot of data. We're not dealing with complex data, but it's a good example to start our machine learning journey. So we're now ready to build the model. So to build the model, what will we do? We want a model that is able to take as an input an image, so one of these, and tell us if it's a coat, a pair of trousers, a dress. And let's actually take a step back on this, because when we do machine learning, as scientists, as we were saying last time, we always want to be aware of the reasons why we're doing things. Like, we don't just want to do things just for the sake of doing things, especially when it comes to the industry. And so why could this be relevant to somebody who asks us, can you make this model? Can you throw some answers in the chat? Like, why do you think this problem is relevant to the industry, or perhaps to Zalando itself? What are some practical use cases of all of this? Okay, so we have our first answer, style forecasting or inventory planning. Can you expand on that a bit, Omer? That's an interesting answer. Mario is saying recommendations for users, maybe. How's that, Mario? How would you use that for enhancing recommendations? Like, let me understand. Like, when would you actually have a look at an image and you would need to know the class? So Clara is saying finding similar products. So very similar to what Mario said. So one of the use cases could be a user is uploading an image on the Zalando website, right? Let's say Zalando has a lot of vendors, and the vendors want to upload their products on the website, right? This also happens with all other e-commerce platforms such as Amazon, but you can also consider this case Facebook or Instagram, right? So a user is uploading an image, and perhaps the user may choose also the category, right? They can say, all right, this is indeed a pair of trousers, or this is a coat. However, the user, for some reason, may lie, or they can do a mistake. And so what we want is when we have millions of users, if not sometimes billions, consider Facebook, right? Or also Amazon. And we want a model that's useful and that can be used to actually understand if the user is classifying the product in the right category, or if instead that product needs to be recategorized. So a very kind of simple problem that can be solved through machine learning. So I see Filippo in Google Lens, but only for this 10 class of object. All right, check out Google Lens if you don't know what that is. Yeah, to recognize a picture, to understand what it is. And so Omar is expanding, saying style forecasting, as in maybe one season sandals sells more than sneakers and so on. As far as inventory planning goes, the image of an item from a vendor can be processed through this algorithm to better understand the traffic in a warehouse. Yes. So definitely, all is super interesting and super relevant to this scenario. So I really hope that this is also interesting to you. I think sometimes use cases are even more interesting than the science behind them themselves. So yeah, so definitely. And this is also used when you want to recognize, like, if a user is uploading a picture that shouldn't be uploaded. So imagine like all the picture that go on Facebook or on Instagram that shouldn't be there, right? So yeah, definitely super important problem. Image classification, where you want to say, for also a binary image classification, you want to classify if an image is not appropriate for, let's say, under 18, or appropriate, right? All right. Let's jump back again into our science. So let's set up the models of the layers of our model. And so taking a step back, what is a layer? So we have studied in a previous seminar that a neural network is made up of layers. And so essentially, layers are a set of neurons that are activated. That's what we say, right? by what is fed into them, the data that is actually fed into them, and then they would produce an output that is then passed on to the next layers until the last layer, which is the layer that actually tells us, hey, this is what I have predicted. And so that is interpretable by humans. This is also why we call neural networks and deep learning a black box methodology, because we feed in the data. As humans, we don't understand much about what's happening inside, meaning that sometimes explaining the weights and all of that is something that it's hard to interpret. And but at the end, what's coming out of the neural network is something that it's human interpretable and readable. So I hope this was clear, and that's exactly what we're gonna do here. So as you may see, our model is a chain of layers. In this case, we only have 3 layers. It's quite a simple model. In the first layer, we have a layer that flattens our data. And so you remember our images are 28 by 28 matrices for a total of 784 pixels. And what we want is to make this one-dimensional. All right, so we have a flattened layer. And then before looking at the middle layer, as an output, we have a dense layer that is a simple layer with 10 neurons. And why exactly 10? That's because the classes that we have are 10. And so what will happen at the end of our network is that only the neuron, only neuron that best represents the object that we are classifying will be activated, right? This is essentially what happens. In practice, what happens is that they all are activated, or almost all, but some are activated more than others, and we'll see that in a second. In the middle, what we do is that we create a layer that has 128 neurons, and one may ask, how do you get this number? And that's essentially the question that you, as a machine learning engineer, should answer. How do you do that? Yeah, that's like a very hard problem. There's hyperparameter tuning and all of that, but it's not interesting for now. And so we choose a higher number of neurons than the ones in the output. And so essentially, at the beginning, we have 784 neurons, which then are fed into a layer of 128 neurons, which then are fed into a layer of 10 neurons. And what happens is we here specify the activation function, which we already went through during our last workshop. In this case, is the rectified linear unit, right? You remember this. All right, so let's actually create the model. Great. And another few concepts that are super important are we need to define what kind of optimizer, what kind of loss, and the metrics to evaluate our model. Now, let's spend just a few words on these because I think they're super important. And as Virginia said, there are already a lot of libraries that solve machine problems. And we are not here to learn how to create those libraries, because if we think about software engineering, it's like learning how to create compilers maybe, right? Or specific like optimized algorithms. And we're not here for that. Maybe that's super interesting, but that's not what we're here for. So what we are here for is to understand what kind of parameters we should put to our models, what is the number of layers and of neurons that we should use, how to evaluate our models. And there's not a right answer to these. Of course, the right parameters are the ones that make the model perform best, but how to do that, there's not a right answer to that. All right, so Hossein is asking a question about the second layer. And Virginia, please feel free to in at any time and add anything to everything that I'm saying, okay? Like, of course. So, all right. So is the number of outputs of the second layer optional, or is there a reason for it to be 128? Well, thing is with neural networks, and Virginia can definitely speak more to this, it's some sort of exploration and intuition at the beginning. So you want to try out many models before having a final model. And in these models, you want to test different combinations of number of layers and number of neurons. Of course, some of them wouldn't make a lot of sense, but essentially by increasing the number of layers and increasing the number of neurons, you're adding complexity to your model. And what happens when you do that is that if you don't overdo that, then your model will have a better performance. But it's very easy to overdo that. And so your model would be, let's say, too strong, and you would end up into overfitting. On the other hand, if you don't use enough layers and neurons, then you will end up underfitting and not being able to have a good performance. So I don't know if Virginia would like to add something on this.
Yeah, exactly. I was typing a long answer in the chat, but I guess it's easier to to say it. So as Jacopo said at the beginning, the number here is arbitrary, 128. You should select something which kind of looks reasonable, but then the true way of building a neural network is actually trying out different combinations. So the number of neurons and in a layer and the number of layers are actually called hyperparameters. These are parameters of your network, which you cannot learn through backpropagation. So you cannot learn them through training, but you learn them trying out different combinations. So building different models. For sure, it's a very expensive task. And in a very ideal world, you would have to try out all the possible combinations, which guarantee a good accuracy of the model without overfitting, as Jacopo said. So we don't want to learn too much about the training set, meaning that we don't want to learn the noise in the training set, which then wouldn't allow us to generalize. But yeah, the ideal way would be hyperparameter optimization. So Jacopo just shared a good resource on Wikipedia to learn about it.
Yeah, definitely. So as you may read on Wikipedia, there are many different ways. It's not really trial and error. Yeah, you can generalize an error, but there are very many scientific approaches. That are not brute force necessarily. They're more intelligent than brute force, but you can definitely go ahead and explore that yourself. Also, let me add that nowadays on the cloud, there are many services that do that automatically for you. And so once you have a model, you can choose to let them handle the hyperparameter tuning on their own. So it's great, right? We have AutoML, that is machine learning, automatic machine learning. You just feed in the data and you specify which problem you want to solve, and it creates a model for you. You also have automatic hyperparameter tuning. So what's left to us scientists? That's a good question. But definitely something is left, otherwise we wouldn't be here. So again, loss, we've already seen loss in our last time together. And so here we choose the sparse categorical cross entropy loss, which I won't dive deep into, but it's essentially a loss that we want to minimize, right? That measures the distance between two probability distributions. If we were classifying only two classes, so a binary classification problem, as we will see in a workshop, we would be using a binary cross entropy loss, and there are a lot of loss functions that you may use. So if you actually go on this link, you can see all of the losses that are available. And of course, you can also specify your own mathematical function for the loss. The most used ones are the mean absolute error, the mean squared error. There's also the Kullback-Leibler divergence. I probably pronounced that wrong, but yeah, so that's essentially it. All right, then the optimizer. The optimizer, what is an optimizer? An optimizer is essentially the way the model is updated, right? In this case, we will be using Adam, but there are a bunch of optimizers also. So you can also have a look at those and dive deep into those. Usually Adam is the one that's used the most for simple, and not only simple problems. It's a good if I don't go wrong. So it's good with problems that have a lot of data, but there are many other ways, and they're mostly based on gradient descent. That is a technique to learn the weights. Finally, we have metrics. The metrics are used to understand the performance, right, of our model. In this case, we'll be using accuracy. So how many images were classified correctly. All right, so ready to, now we built the model, we're ready to train our model. And so to train a model, what do? We feed it with images, right, with data, in our case it's images, and labels. So let's not forget that we not only feed it with images, but also with labels. And we specify for how many epochs we want to train the model. So you can think of epochs like epochs in history, right? Where each time the society would evolve. So the same happens for our model essentially. And so we launched the training of the model, which being a very simple model and with not a lot of data will not take that long. So while we wait for the model, let's have a look at what's happening here. So what's happening is that we are processing the images, right? And it's telling us the time that it takes to execute the model training, and also the loss that is calculated at each step. And finally, you also have the accuracy of the model at that step, right? So now the model finished training. As you may see, the loss went down from 0.5 to 0.23. And this is not always the case, like the loss being a, do you say monotonic in English? I guess monotona in Italian function, right? Where it just decreases. Because it could also happen that for some epochs, the loss actually increases and then it goes down. And why could that happen? And that could happen because the model is exploring some possibilities, so some weights, and it then learns that they're actually not necessarily the best ones, right? So that could happen. All right, so yeah, we can see that the accuracy reaches about 91%. And now we can finally use the test set to evaluate our model. So here we pass into the evaluate function the test images and the test labels. And so the model will only use the test images, and so make predictions on test images, and then use the test labels to check if they did well or not. And so we can see that this is the loss that's being outputted. This is the accuracy. And so this indeed is the accuracy that we get from our model. So noted, probably the accuracy is a bit, the test accuracy is a bit lower than the training accuracy. And so you might wonder, why is that? So as we can also read, this can be a symptom of overfitting, right? So in this case, the accuracy is not very much lower. And so personally, I wouldn't classify it as overfitting, but it could suggest overfitting, right? And so our model is doing very good on training data, but it is doing a bit worse on test data. All right, so now we can of course use our model that's trained to make some predictions on the test images, and so we can see what actually what is the output of these neurons. So as you may see here, we predicted all of the test images. We made our predictions. In fact, if we say predictions.shape, right, we see that we have 10,000 images that are predicted, and each has 10 values. And why is that? Because these are the 10 neurons in the last layer. And what does one of those look like? Well, here it is. We can see how, and these, please note the e to the, or the exponent to the -7. So this is a very little number, very little number, very little number, and so on and so forth until this number, which is actually 0.95, right? So yeah, maybe I can also do round, let's see, this to, will it work? No, okay, it's fine. Maybe round export anyway. So we can see what's happening here, and we can see which neuron is the one with the greatest activation, and it would be this last one, right? So index 9, we use the argmax function. And so as it says here, the model is very confident that this image is an ankle boot, that is class names object at position 9. And so let's actually see that in test labels, if we choose the first label that would correspond to this index, right, it's actually 9. So our model did quite nicely. Here we only define a few functions to plot and to display images. And so as you may see, this is what we were looking at just now. And this is the activation of the 10 neurons that we're considering. As you may see, essentially one of them is activated. We can also plot a few images, right? And we can see the performance of our model. So this is a pullover, 99% confidence that this is a pullover, 100% confidence that these are trousers. And yeah, this one, yeah, 79, okay. 79 also for this sneaker. All right. And yeah, so what happens then in production, right, when you have, yeah, the results seem to be very good, Hossein, indeed, because the choices that we made, well, we made the the authors of the tutorial or workshop made were quite nice, right? So on the number of neurons, the layers, the classifier and the metric that were used to evaluate the model and all of that. So yeah, we grab an image from the test data set and we predict the label for the image. as you may see, this is the label that is predicted. It doesn't show the image, unfortunately. It's fine. Anyway, it predicts it's a pullover. So yeah, this was the expected. So this is what it's being predicted, and what was expected. It doesn't show it to us, but it's fine. Like it just predicts what it is. So maybe we can, let me see if I can plot the image. Maybe this should be it. Not entirely sure this would work, but we have a little bit of time. Plot image, and we wanna it's from test image 1. Okay, so it would be I equals 1, predictions 1. This should work. Yes, fantastic. All right. So yeah, it is indeed a pullover, and this is what's being predicted. Yeah, here it is. Okay. So Virginia is asking, any ideas on how to prevent overfitting? Yes. So please share your thoughts. I don't see any answers to that, but I'm sure somebody has some ideas. So how would you prevent overfitting, like in this example? And we've already briefly talked about this.
Yeah, I think maybe we saw this in the first course. For example, let's see, go to says choose significant data. Well, I mean, ideally, if we had a perfect training set, perfect images, we probably would have even a perfect model. This is in a very ideal world, but typically data sets contain noise, and during training, we learn that noise. So when we see new images, we're not able to learn anything from them. Let's say, for example, images which maybe have, for example, images of a shirt. Let's see, they are horizontal instead of vertical. At this point, probably maybe the model, if it hasn't seen any example in the training set, it will not be able to make a good prediction. Let's see, maybe test on a smaller batch of items and for less epochs. So there's less noise. Okay, sure, there's, well, not necessarily less noise, depending on the sample you got from the training set. And also, if you're learning on less data, you have less examples to learn from. So it's harder to learn. The more data, the better usually. Much more diverse batch of items. Okay, this is one direction. Okay, by diverse match of items, you mean, in a technical term, we can perform data augmentation. So data augmentation basically is a technique that allows you to increase your data set, as it literally says, and you're trying to produce some synthetic data. So for example, let's look at this MNIST data set. What can we do to augment it, to have more samples? Well, some techniques are, for example, let's pick the image and rotate it, or let's change the color, or let's add a small noise, like some points. So all of these techniques, and there are many, are called exactly what Jacopo is showing right now, is data augmentation. So here you see the picture. You're changing the butterfly, for example, you're removing color, you're flipping it, rotating it, and as a human, you see that it still is, and it looked like a butterfly. So you want your model to learn that as well. And yeah, or otherwise, exactly. We're actually doing some work there for Google to labeling work, which we talked the other time, which is kind of a big problem. Or another techniques, I'll mention it briefly, is using a validation set. So what is a validation set? Basically, when you're performing training, you're actually using another data set, which is the validation set, to test your model at each epoch. And why do you do this? You do this because you want to stop training when the validation set tells you that it's not accurate. So typically what happens is that in the first epochs, you're going to get a lower and lower loss on the training set because you're learning. And at the beginning, even the loss on the validation set should decrease until a certain point where you learned to generalize enough on the training set. And then at that point, you start learning the noise. So the validation loss will start increasing. So try to look, there are many resources on this about validation and all the different techniques, but this is one thing that wasn't in this code, for example.
Yeah, thanks a lot for all of that insight. Well, in the meantime, I was trying to add a lot of layers and a lot of neurons to our net, but it seems like the performances are actually similar. And yeah, this is probably because our data is quite ideal and is not very, the variety is quite, like the variance in the data is quite low. And so you'll get a right model regardless. But if you try that with actual like real data, like more generic data, then you'll see that also adding one layer can totally change the performance. So yeah, fantastic. Then I would say let's now move on to transfer learning. If there are any questions on this, and we'll go quite faster on transfer learning, also considering the time. Can you please type in the chat this was helpful for you, or like on a scale from, let's say, 1 to 10, because yes or no is not the best answer for this, but on a scale from 1 to 10, how useful was this for you, considering also if you've seen this before or not, so we understand and you also can evaluate for yourself if this was useful to you. Where 10 is like super useful, 1 is like, nah, I would have rather watched a TV series on Netflix. Okay, so Filippo says 5. Aries, we have a 7. 9 for Hossein, that's nice. 8, 7. Okay, so it's great to see that for some of you, this was quite helpful. And so we're really glad that you enjoyed it, and I'm sure you will enjoy even more our transfer learning workshop in a second. Because transfer learning is actually used quite a lot, because if we already have something that was trained by somebody else, why shouldn't we use it, right? It's not necessarily like this all the time. So let's have a look into transfer learning. All right. So let's jump into this. I'll ask somebody from the team if they can post the link into the chat. And you will jump into here. But before we go here, let me share a few slides on transfer learning. All right, so we have just trained an image classifier in which we fed our model with images. Our model learned how to classify those images based on some classes that were fashion genres or types. So we won't recap what TensorFlow is, right? Now we'll look at cats and dogs. That is one of the most common problems in machine learning, that one may say, oh, it's always cats and dogs. In reality, it is super useful to understand this in order to have a good understanding of all the other more difficult and generic problems. And some of them, it's quite hard to understand if these are dogs or cats. So also for us humans, it's not always easy to classify these images. All right. So in general, when we look at machine learning, this is the pipeline that we look at, right? We start from a use case. as I always say, we always want to identify what is the problem that we're trying to solve. Sometimes not having that clear and actually maybe solve or not even solve the problem. So solve another problem, right? And so you want to define an objective. And usually when you do that, especially in the industry, but also in research, you want to define some metrics of success for your problem. So you don't want to say, oh, I want a model that recognizes if this is a cat or this is a dog. I want to define some metrics, such as I want a model that has this amount of accuracy, this amount of recall, and all of that, because my model will be better than the one that is the state of the art, right? We don't just want to say, I want to model that. Also because usually that already exists. And as Virginia said, the deep learning is actually better than humans in many image classification tasks. And yeah, I wouldn't actually doubt that. Yeah. So the RoboCheck images are machine learning proof. There's a question. What do you mean, Gregorio? Do you mean the CAPTCHA ones, if they are machine learning proof? Well, I must be honest, I don't know if they are. So I don't know if Virginia, you have some insights on that. For sure, like some models that are able to identify all of the images that are like I don't know if you look at like which ones of these images is a truck. I don't know.
CAPTCHA is more of even gathering labels from humans and getting some sort of like a feedback loop. So you're getting users to label images to improve a existing machine learning model.
Yeah, definitely one of the ideas that it's behind CAPTCHA, and I think it's a fair price that we can pay. But I think that what happens there also is perhaps the models that are used to trick CAPTCHAs aren't necessarily performing 100%, whereas humans may perform quite well on those. And so one would say, one that designs those CAPTCHAs would say, if you also miss one image or one or two images, which could be the case for some fairly weak models, then that's not good. Another CAPTCHA methodology that I've seen lately on Binance, I don't know if you know, Binance is like for trading cryptocurrencies. It's sliding a puzzle piece on in the right position, and so that's what they use. Yeah, and so super interesting. If somebody has more info on that, please share it. That would be quite interesting to know more about. Anyway, let's go back because we don't have a lot of time. So we want to define the objective of our machine learning problem pipeline. And of course, the most important part is, or the most, let's say, scientific part is the one highlighted with the red box. That would be that of collecting the data. That is not necessarily scientists do. They usually already have the data. But as Virginia said, we explore data, we prepare data. That means we also exclude data, we transform data, we augment data. And then we want to, once data is ready, to build our model, train it and test it, and finally use it to predict and evaluate it. And this is not the end, because it's a feedback. There's a feedback mechanism here where you go back and you say, okay, this is the performance of my model. Your stakeholder would say, all right, this is good enough for now. Let's put this model into production, but let's improve this over time. And so you might want to spend some more time into optimizing hyperparameters, or I don't know, feeding it with more data, checking out the performance over time, and all of that. And also you want, of course, go back to your user and understand the use case changes over time anyway. What transfer learning does is that it adds a step to this pipeline while actually removing a step from the pipeline, I would say. So as you may see, we have these two new steps, or the training step that is essentially based on the concept of the reutilization of a model that was already trained by someone else. So this is exactly what we're going to do today. But what is a pre-trained model? So essentially it is a model, so a network, right? A neural network that was already trained by somebody else on a large data set. And the model is actually saved into a file that you can then use into your own model. Because let's make this clear, once you have a model, you build it with the layers and with the neurons. And what you're learning, if you remember from our previous classes, you're learning the weights that are on the on the arrows, essentially, that are connecting the neurons, right? So the weights of the functions that are connecting. And so you can save those weights and then upload them back into your model. So essentially that's what happens when you save a model. And so usually the models used in transfer learning are trained on very large data sets and are then used for smaller tasks. And that's exactly what we're gonna do today, right? So we will be using a model from Google that is ImageNet, or a variant of ImageNet. That's what we'll be using. That was trained on a very large data set with its output labels, its output weights, and we will be using that on new data. That in our case, it will be cats and dogs. All right, so I hope there are no questions on this. So let's move on to our activity. So open the notebook that we pasted in the chat, and that is also pinned in the chat, I see. And so this should open up. Click on Run in Google Colab. And then let's connect to the Google supercomputers. So in this exercise, we will actually be first training the model using the pre-trained model by Google. And we will be fine-tuning our model. And we'll see how to do that. So as usual, we import some libraries and we pre-process the data, we download the data and all of that. So as you may see, the data is available online. You can download it. There's quite a lot of data this time. We are in the millions, so 68 millions. Yeah, I don't know. Actually, I'm not entirely sure that this is the number of data. I think this is actually the size of the data. My bad. All right. Anyway, we now build the train data set and the validation data set. We take that from Tensorflow, and essentially we have our directory here. We take the images from that directory, and what we want to do is that we want to specify a shuffling in the images. And that's super important to avoid any bias in the data. That's one of the steps that you can take to avoid bias in the data. So you would just want to shuffle them around. So let's have a look at these images. As you may remember, the first step that we always want to take in the machine learning is to actually explore our data, understand our data. And I don't know about you, but I really love both dogs and cats. And yeah, here we have some cool images of dogs and cats. So just as before, images and labels. Just this time, the problem is simpler as we only have 2 classes. So it's a binary classification problem. But it's a little harder because, as you may see, there are also colors in these images. And perhaps the data set is not, the quality of the data set is not the ideal. As you may see, for instance, this dog is not front facing, right? And so it could be mistaken by a cat, by our model, probably not by a human. And sometimes we also have humans appearing in the picture or other objects that might confuse our model, such as this thing over here. All right, so essentially here we will be, let me also do this. So we will be dividing our data into training, validation, as Virginia was explaining before, and test set. So we can see that we have 63 batches. This doesn't mean 63 images of training, 26 batches or groups for validation, and 6 batches for test. Okay, so yeah, just ignore that for the time being. So here, we're actually going to use a technique that Virginia just explained, data augmentation. So since we don't have a very large image data set, considering noise that we have in the data, we can artificially produce some samples to allow for diversity in our data, still maintaining reality, right? We're not creating, I don't know, tables essentially. And we're going to do that by applying random flip and random rotation to our images. So a random flip, and a horizontal random flip would mean flipping the image horizontally, such as what happens when you take a selfie and you're like, oh, this is what I look like from the selfie perspective. Yes, because it's like flipped. And then the random rotation applies a rotation to the image. And so this, we define these steps, right? These are steps in this variable. Now, we apply these, for instance, to an image just to see what happens. So we take an image, as you may see, the image is both flipped and rotated randomly, right? So it's not the frame that is rotated, that would still be a square, but it's the image that is flipped, right? Or so this should be clear. Okay, so again, also here we rescale the pixel values. This time instead, we won't be scaling them between 0 and 1, but we will be scaling them between -1 and 1. And that's because this is how it was done in the net that we were going to use. And so we should feed into it the same data that it expects, right? There's some sort of SLA, so a service level agreement or API that we need to respect. All right, so yeah, so we just rescale the data here, we divide it, and so we have the scaling that is done. All right, so now we're ready to talk about the base model that is essentially MobileNet v2 that's based on top of ImageNet. There are a lot of papers and resources about it. Feel free to go on the internet and read all of them. I would actually encourage you to do so. Or another way to have a better understanding of them in your own time is also looking at practical applications that were made on top of those. And you can find a lot of open source code or also videos or articles that actually talk about these. So don't be shy and go ahead and use them. So what we're doing here is that we're creating our base model that is loaded from a pre-trained model that is MobileNet v2. we're feeding it with the image shape, right? That it should process. And then here, what we are doing is that we are loading, as it says here, a network that it does not include the classification layers at the top, right? And this is super like useful to allow our model to be used by in the specific use case that we want to solve. Okay. Anyway, so we create the base model, and here we have the feature extractor that converts the images that were 160 pixels by 160 times 3. The 3 is because we have colors, and so we need for each pixel one value that is in the RGB model, right? So red, green, and blue. And so we convert these images into a 5 by 5 by 1280. So we just convert it into this format because it's what it's expected. And so what we'll do here is that we'll be processing essentially these images. So now what we do is that we call it freeze the base. And why do you do that? You do that because you don't want to retrain the pre-trained model during your training. Otherwise, you wouldn't be using the pre-trained model. You would only be using the model that was built by someone else, but that was not trained on someone else's data, right? So this should make sense. Again, we're freezing the model that we imported, so the MobileNet v2 model, so that part will not be retrained. And of course, this is quite intuitive why this is important. However, just in a few minutes, we will be making that trainable. So let's see what happens. All right, so you can see the model. As you may see, it's not at all simple. So by say model.summary, we can actually have a look at what happens here. And we have many activation functions, the size, it's quite different layer by layer. And so in the end, we have a model with more than 2 million parameters, which is quite a bit. All right. Now, now what we need is to add another layer that we will call the global average layer that will allow us to convert the features to a single vector, just as we did before, right? Essentially, it's a pooling. It's not really what we did before, where we flattened it, but the idea is a bit similar. So we are actually pulling some features from the image, right? So that we transform it into a lower dimensional vector. All right, so we then finally add a layer to our network that is a dense layer with only one neuron. And why do we only have one? That's because we are in a binary classification problem. That is, is it a cat or is it a dog? And that's why we only need one neuron, activated or not activated, okay? All right, finally, we're ready to make our model. And how do we make our model? Well, we chain all of these, right? So everything that we have talked about until now. So data augmentation, that's starting from the inputs, right? That essentially the specification of what the input looks like, then the preprocess step, then the base model itself, where we specify training equal to false, then the global average layer, where we pull some features, and then actually here we're adding also a dropout layer, and very quickly a dropout layer essentially turns off some neurons randomly, but you can read more about it, and it's used also to avoid overfitting, if I don't go wrong. And finally, we have the prediction layer, that is the last one. So finally, we have our model. So we can compile our model still with specifying optimizer loss and metrics that are actually the same as before, but with binary cross entropy as I was specifying before. This is our model. And finally, we can train the model with 10 epochs and also evaluate. While it trains, we also have only 5 minutes left. Do you have any specific questions that perhaps we can take after the end of the workshop? If so, please write them down in the chat and we will try to answer them. All right, so we can also then plot the learning curves of the model as soon as it finishes training. It will just take a minute. Right. We will actually see, as soon as it plots them, that the training and validation losses will decrease over time as epochs go by. So we'll give it a minute here. And yeah, if you're wondering what then a machine learning does in their day-to-day job, they don't necessarily focus on the complete pipeline. They might also only focus on the structure of the model, or perhaps on the evaluation and the fine-tuning of the model, or also maybe only on data exploration, data augmentation, and all of that, and like denoising. Or sometimes, such as what happens for me and Virginia also, we focus on the complete pipeline, which of course takes more time and doesn't allow you to focus maybe a lot on a specific aspect of the model. So it really depends on your use case. Anyway, here we plot the training and validation accuracy. As you may see, the accuracy goes up as time goes by, and the loss goes down as time goes by. However, we can still see a gap in between the training and the validation loss, which we really the best situation, and same is happening for the accuracy. We would like the difference between the training and the validation loss to be as little as possible, and also the loss, absolute loss, not to be high. And so what we will be doing very quickly is to fine tune our model, where we say, okay, let's go ahead and unfreeze what we froze before, right? So let's take MobileNet and say, all right, thank you for providing me with this fantastic model, but now I need something that is even more powerful than what you provided me with. And so that's what essentially we're doing right now. We are unfreezing these the weights, so the training steps for the model, starting from a certain epoch, so that our model, starting from a certain epoch, can start to train itself also in the base model part. And so this would it would increase the performances of the model. So at the beginning, again, we're keeping the epochs, see, initial epochs. We're training the model frozen, and then we are unfreezing it later. And so once the model is trained, As you may see, we are executing epochs 10 to 20, and not 1 to 20. You may see the accuracy is actually going up, and the loss is going down, which is good. Again, here we have the validation loss, not the test. So we both have the loss, that is the loss on the training data. The validation loss, that is loss on the validation set. And then finally, after we're ready, so after we have done all the fine tuning, we will be evaluating our model on the test data. That is data that was never seen by the model. Okay, so it's like the final test. So let's say a validation set, it's like the quizzes, practice tests that you may do like during your studies, and instead the test set is the final test. All right. And yeah, Virginia is also specifying that that's actually true. We're seeing better accuracy on the validation, and this is actually very, very rare. We have the opposite usually. So yeah, thanks for specifying that, Virginia, in case you're wondering. But it could happen as it is in this case. So as here, we may see how the training then started around epoch 10 with the fine tuning, and you may see how the accuracy goes up, right? Also, you may see what happens here. We have the loss that's actually going up a bit. And as I was saying before, this may happen because your model is exploring other possibilities. So just like a baby that learns how to walk around, they learn they can go faster, but then they perhaps fall, but they learn that they can go faster. And so next time they will go faster, but be careful about it. And so as you may see, this is what happens here, right? Okay, so we may also see that the distance between the losses actually decreased, right? Super good. And finally, we can verify the performance of our model. And so the test accuracy on data that was never seen by the model is 98%, which is quite a lot. And finally, we're ready to use our model to predict if the image is a cat or a dog. Right, so these are images from the test set. All right, so it seems like nothing went wrong in these tutorials and stuff. Yes, the accuracy 98% is actually very nice. And what you can do if you're super interested into all of this, or you have some spare time, is try to make something that performs even better than this. Because it's probably not that hard if you actually look at perhaps some other pre-trained models that are maybe even better than ImageNet, MobileNet. Fine tune it. You can increase the number of epochs perhaps, or I would leave it to you, to be honest, as an exercise. And as we're already out of time, I would close it by thanking you for the attention, hoping that now the satisfaction level is even higher. So if you want to put your 1 to 10, let's say usefulness, or 11 out of 10, great. Quite happy. But your vote counts actually a lot. But I know I know you're also super interested in all of this. So yeah, Filippo. Okay, 8. That's good to hear, Filippo. I think you were the one that didn't find the previous one super helpful. You probably already saw that, so that's probably why. I see nines. So that's super good for us. So we know that this is actually helpful for you, and we will be able to run the next even better. So yeah, if you're interested in image classification, image captioning, image classification is what we've done until now, make sure to tune in for our last event on Thursday at 6. that Virginia will be hosting. It's super interesting. Image captioning is like super important. It's even it's even harder than image classification. So I'm also super excited for that. And yeah, I don't know if Mario or Virginia want to add anything to all of this.
Yeah, no, I think it's going to be exciting on Thursday for image captioning. So it's quite a complex task. So for an intermediate workshop, it still is quite hard. But I think it's interesting to see the potential of machine learning and how it can learn from any type of data. So from images to text to numbers and combining them. So I think that will be quite fun. Also, it was part of my master's thesis. It's not only on image captioning, but even on another part. But it's a topic I think I mean I like really much and I know about. So hopefully I will be able to explain it to you guys.
Awesome.
Very good. Very good. So I would like to thank you both for being here today. This was extremely interesting. And I will definitely like try and play around with it for a while and see how it goes. I am expecting very bad, but anyway, we'll try. And thank you all for participating. And we hope to see you on Thursday, which should be even better. I don't know. They said it. I have no idea what they're gonna bring. So thank you very much, and we'll see you on Thursday. Have a nice evening, everyone.
Yeah, and as Jacopo said, we can connect on LinkedIn if you have any questions, even besides the workshop on working in the industry of machine learning. Just go ahead and ask us. Right.
Bye-bye. Ciao.
Have a nice day.